Good morning, everybody. Okay, today we're going to start on the second section. Limits of a function and limit laws. What do you think what is a limit? When we say limit, what are we talking about? With what we discussed last class. What do you think a limit means? You've heard people say, I've reached my limit. I can't do this anymore. What do you think it means? Yeah, it's pretty much how far you can go until what? Until either it gets fixed or either the solution or can't go any further. And that's what limits are. We do the same thing here. So, for example, what's the domain of that function? You're dialing a phone in there. That's exactly correct. The graph of this function looks like this. The domain is from negative infinity to 0, and then from 0 to positive infinity. So in other words, we know that everywhere else except 0, a value exists. So the only question we have is what happens at 0. So that's typically what we do a limit. When we look at limits of functions, we look at what happens to the function at the most inopportune time. So we're going to look at what happens when we get close to 0 of this function. So in your own words, what do you think happens? Okay, now, and okay, stop before we mess up everything. If you notice how they're set, they're like this. So take each stack separately. They're not separated in different pages. There should be 3 pages. If you don't have 3 pages, then keep on looking because you did something wrong. Look at the bottom of the page. There should be numbers. 1, 2, 3. And don't tear up other sets to complete yours. Somebody obviously messed up the set. So if you mess up, what's that? Well, where's the third page of that? Somebody must have 4 pages then, or 2 pages. Okay, then there must be one. Whoever took the one before yours must have screwed it all up for us. You look in the bottom of the pages, you see 1, 3, 5. There's 3 pages. They're double-sided. There should be six pages total. It's not that difficult. So whoever screwed it up the first time, please pay attention to what you're doing from now on. So the way we would look at this is we would look at a limit of a function. We would write it this way. This is what we're looking at today. So what do you think this means? How would you answer this? What are you going to tell me? When x approaches 0 to this function, what happens? How do you mean? Yeah, but we're not saying x equals 0. It says x approaches 0. What happens to the graphs? That's what it means. That means our x's are getting closer, 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 closer to 0. That's what this says. But what's happening to the entire function? What values are they going to? Look at the picture. That's why the picture. That's why I told you all last week when I went to library functions. Memorize those. It's going to help you so much learning this stuff, making it going much easier. Because if you don't remember what this looked like, you're going to have to graph it. Does it? Everybody agree? That's our answer. You got 50. You got half of it right. How many ways can you approach 0 on the x-axis? One from this way and one from this way. Does the graph go the same direction, both of them? If I go this way, what happens to the graph? Where does it go? Goes towards what number? And if it comes in from this side, it goes to positive infinity. These are different answers. Positive infinity is not the same as negative infinity. You can't just say infinity because we have to be more precise in this class. Let's think about it. It's engineering. You eventually you want to become engineers. So you don't say, oh, it's about 4. Build it, see what happens. So no, we're looking at that's what we're looking at here. Sometimes we'll get an answer, sometimes we won't. So when something like this, since both sides go different directions, we say it doesn't exist. The limit does not exist because when we look at it from both directions, it doesn't approach the same thing. So our first example, well, let's look at our first example. In our sheet. How does the function f of x delta y over delta x behave near x equals 1? This is what it says. It says, what happens to this function as x nears 1? Which what it's saying is, as x, the way you would read this is as x approaches 1. Remember, mathematics is a language. We have to use the same language everybody else uses. Because if you're going to communicate to anybody in mathematics, it better be in the same language. So we read this as, you can't say x point the arrow 1. It says as x approaches 1. So what do you think happens to this function? Are you sure? Actually, you'll be surprised in this one. You'll be surprised in this one how this one really looks. So let's look at this function. Algebraically, just remember, I told you, calculus is only the first step. Everything else after that is algebra. So with this one, can we do anything algebraic to this equation. We know that if we let x equals 1, what happens to this function? It becomes what? What's on top? What number? Over. Whenever you have 0 over 0, that's actually pretty good. Because if it's 0 over 0, that means that they both have this in common. Can we do anything to the top equation? Can we factor it out? What does the factor do? Yeah, because this is the difference of two squares. The difference of two squares is that. So you're right, it becomes x plus 1, x minus 1 over x minus 1. We can remove x minus 1. You know what that's called? But what happens at 1? It's discontinuous, right? So this is called a removable discontinuity. Discontinuity. It's a removable discontinuity. Because what happens here is our function now looks like this. What does that graph look like? What's the y-intercept? The y-intercept is 1. The y-intercept, what's the slope? It has slopes are fractions. So what's the slope? It is 1, but how would you put it as a fraction? 1 over 1. So the slope is 1, or 1 over 1. So from here, go up 1 over 1. There's the graph. But that's what this graph looks like. Remember, we removed the discontinuity. Set that equal to 0. So at 1, x cannot equal 1. X cannot equal 1, because if we do, it blows up the whole thing. So what we have here is we have a hole in our graph. This is a hole. The graph cannot go through that. It can go up, jump over that, and go further. That's what happens when you have a removable discontinuity. So the point 1, 2 is removed. Because at that point, remember, we cannot use 1 in the original, so x cannot equal 1, so we cannot use 1. What value is that? It's at 2. So that's what we're looking for, is algebraically what happens with these things. That's what we're going to look at. All functions will not be this straightforward, and we're going to have to go over. I'm going to teach you. How many of y'all remember from algebra partial fractions? Okay, no problem. I'm going to cover everything we need to make life easier for us. I know you probably heard it before. I hope you heard it. If not, then don't worry about it. We'll fix it. So, as our example sheet says, an informal description of the limit function is this. That's an informal definition of what a limit is. And it's read the limit of f of x as x approaches c is L. Okay, so far so good. So that's what we're looking at. That's what we'll be dealing with in this first part of the course. The next example we have, if you read the very top of it, it says, the limit of a function does not depend on how the function is defined at the point being approached. The limit of a function does not depend on how the function is defined at the point being approached. What does that mean? The limit of a function does not depend on how the function is defined at the point being approached. So what do you think it means? We all read English. So what do you think it means? Yes. Yes. That's exactly what it means. So this is our C. This number here, that's the value we're looking at. So at our last example, we looked at that. This number here is 2 because our function is x plus 1. This is our L. So the concept of limits is it doesn't matter what happens there. It just has to approach a value. So if I look at all the numbers coming up from the left, what are the y values approaching? Remember, the limit is this one. As I approach from the left, what are the y values approaching? They're approaching 2. They're approaching that limit. And same thing, if I approach it from the right, so all of these, as I get closer to C, where is that answer approaching? 2. So we would say here the limit is 2, even though we never get to it. Because we cannot use 1, but we're still saying the limit's 2. So that's the important thing about a limit concept. It doesn't have to exist to be an answer. That's the part that you have to first get through your head because it's counterintuitive what we're taught. This is, if I put 1 in there, it's undefined. Yes, but that's not what we're looking for. We're not looking for a specific value. We're looking at for a limit. What value is this approaching? So as x approaches 1, L approaches 2. That's what it's really telling us. Okay, for example 2, look at the 3 functions. What can you tell me about those three functions? So in A, what's happening at A? How would you interpret that one? This is the first one we just did. As our x's approach 1, what does our limit approach? That's how you would interpret it. Because even though everything's defined except that here, the limit as x approaches 1, the limit approaches 2. Even though it's not defined at 1. Doesn't matter. It's the limit approaches. How about B? Ooh, good question. Is the limit the whole or the black dot? Yes, because the limit is not what happens at 1, it's what happens to the rest of the graph. Where is the rest of the graph going? It's going closer to 2. So that's your limit. And same thing from the other side. It's approaching 2. So the limit is, as x approaches 1, the limit is 2, even though, what is g of 1 in our example? 1. Because it says when x is 1, the answer is 1. So the limit does not, the limit 2 does not equal the actual value of the point. And the last one. Ah. Does it have a limit? What's the limit? Yeah, the limit, as we get closer to 1, the lines are approaching 2. So the limit is 2. And what is h of 1? 2. Here's 1. There's 2. So fortunately, that one works. So here the limit is 2, even though the value is undefined. The limit is 2, even though the value is not 2 at that point. So again, here's the concept back to what I said. It doesn't have to be at that point. It simply has to approach that value. That's the important thing. It's what value does a function approach the closer I get to that C value. That's what I'm looking for. As illustrated by the three functions above, equality of limit and function values captures the notion of continuity. Now we're getting close to defining the concept of continuity. If I asked you to define what is a continuous function, what would you say? Okay, that's one way, yeah. What's another way? If you're graphing it, how would you say something is continuous? I have a squiggle. Well, yeah, I never pick up my pencil. If I start a graph in Infinite, yeah. If I pick up a graph, if I start my graph, I don't care what the graph is, and I never have to pick it up, then it's continuous. Or it says there's no break anywhere in there. Every value is defined in the domain. And now we're getting closer. So if a function is continuous for every value in the domain, if all the values exist. So we're now is f has to be continuous for all the stuff to exist. The process of finding the limit can be broken up into a series of steps involving limits of basic functions, which are combined by using sequence of simple operations that we'll develop a little bit. We start with two basic functions. These are our two basic functions. The identity function, diagonal line, f of x equals x, or y equals x. We find limits of the identity function and for the constant function as x approaches c. Why is this called the identity function? Because no matter what I put in, I get the same value out. It keeps its identity. If I put 1 in there, I get 1. If I put -1, I get -1. If I put 0, I get 0. That's an identity function. If f is the identity function, f of x equals x, then for any value of x, the limit exists, and it's that value. It's whatever value we're going to. The next one is the constant function. What is a constant function? Give me an example. Y equals, let's say 2. There are no x's. Since there are no x's, we cannot have a x-intercept. And if we can't have any x-intercepts, then these are horizontal lines. The slopes are 0. There are horizontal lines. So the limit of a constant function is whatever that constant function is. So even if I say I'm going to C, what is the y value? It's k. So those are the two easy functions. A function may not have a limit at a particular point. A function may not have a limit at a particular point. We just saw one of those earlier, 1 over x. It doesn't have a limit at 0. Some ways that limits can fail to exist are the next example. None of these limits below exist as x goes to 0. So example 4. Let's graph that one. So it says the function u of x is equal to 0 when x is less than 0 and 1 when x is that should be greater than. Yeah. So if we graph this function, what would it look like? What kind of function is this? What is it called? What is its name? What kind of function is it? It has multiple parts. What's it called? Piecewise defined function, yes. These are what are called piecewise defined functions. They're called piecewise because they're defined in pieces. Here's the first piece. For any value less than 0, the y value, these are the x's, the domain, and here are the y values, the range. So for everything less than 0, so it starts at 0, and the rest of it is 0, going to negative infinity. Actually, no, we have to make it because this has to be greater than equal to 1. Because the statement we made earlier, none of the limits below exist as x goes to 0. So it's got to be greater than. So the second function of this piece, our second piece, says whenever x is equal to or bigger than 1, the answer is 1. What if we had, instead of 1, what if we go back all the way down to 0? Yeah. Is this a continuous function? What's the domain of this new one? Yeah. Negative infinity to positive infinity, all real numbers. Because can x be negative? Can x be positive? Can x be 0? So it's all real numbers. So, and that's, well, it sounds continuous to me, but what happens at 0? This is what is called a jump discontinuity. It's a jump discontinuity. At that point, there's that's where there's continuity. I have all these points here, but at this one, I got to jump up, and it goes on forever, ever to positive infinity. So discuss the behavior of the following functions. Explain why we have no limit. Why is there no limit as x approaches 0? Thinking back to our first example. Thinking back to our first example, what do we notice? What do we, looking back to the first example, did we have a limit there? Even though it didn't exist at 1, we had a limit. Why did we have a limit in the first example? Very good. Exactly. In the first example, as we were coming from the left side, it was still as x was approaching 1, the limit was going to 2. The y values were going to 2. Same thing on this side. As we're going down this way, the y values are going close to 2. So that's the first observation. For a limit to exist, it has to approach the same value from both directions. Does this example do that? From the left-hand side, what value is it approaching? 0. As x approaches 0, y approaches 0, or y equals 0. So it's a constant function. On this side, as x approaches 0, y approaches or equals what number? Are they the same? No. Since they're not the same, the limit doesn't exist. That's why there's no limit. Because the graph approaches 2 different values as x approaches 0. Because that's one of our conditions. If you have a limit to exist, it has to approach from both directions. The second one, b, g of x. When x does not equal 0, the function is 1 over x. When x equals 0, the function is 0. All right, so our b. G of x says whenever x does not equal 0, we use this function. Whenever x equals 0, the answer is 0. So let's look at the graph of this one. What does this mean when x does not equal 0? What x values are we looking at? Everything to the left, everything to the right. So everything to the left, all the negatives, what does that graph look like? That's the negative side. When x is negative, the function is negative. On the right-hand side, that's what this graph looks like. Again, memorize your library functions. At x equals 0, the answer is 0. Why doesn't the limit exist there? As x approaches 0. So what would you say your answer would be? Why does the limit not exist as x approaches 0? If we're coming from the positive side, where is it going? Where? It's going to positive infinity. So that's from the right-hand side. From the left-hand side, it's going down to negative infinity. Are they going to the same place? Is it anywhere near zero? No, that's why. Because they're going farther away from what is the actual value. So that's the reason that one doesn't exist. Example C. F of x is 0. Oops, that should be whenever x is less than equal to 0. Gotta fix that one too. And the other one is we use sine 1 over x whenever x is greater than 0. There were two things I got to change here. There's another one. It should be 0. And that page, I got to change that page. So what do you think the graph looks like of this one? It's a sine function. What do we know about the sine function? Yeah, all these are the y values here. These are the y values. These are the x values. So what do we know about the graph of sine? Does it have a limit or bound? It's between what numbers? 1 and -1. Right. You had it right there. If you think unit circle, the highest it could be is 1, the lowest it could be is -1. The sine deals with the y values. And okay. So when x is less than equal to 0, the answer is 0. What does that look like? So what happens at 0? The answer is 0. It's a dot. And any other x values to the left is 0. So it goes to -infinity. So on this side, the limit as x approaches 0 from the left-hand side, what value is it approaching? 0. Now the sine value. When x is greater than 0, what happens to this function, 1 over x? The bigger x becomes, what happens to this value, 1 over x? It becomes smaller. So that means the smaller x is, the bigger this value is. So what this function looks like is not right. It's still bound, but it tapers. When x is small, it's very sporadic. It very goes up and down. But as x gets big, this number gets small, it gets spread out further. The period becomes longer. So what does that limit approach? And for these type of problems, I don't mind if you use a calculator to graph your picture. I don't expect you to memorize all this stuff. So if you see a function of that, graph it and see what happens when x is positive. And what you'll see is a very, very sporadic, and then it starts easing off. It's still going to be between 0, 1 and -1. So does this function approach any limit? Oscillating function approaches positive and negative, whatever those values are, whatever the highest and whatever the lowest. That's a oscillating functions do not have limits. So this one the limit doesn't exist because it doesn't. And are they the same? No. So far, so good. So what have we discussed so far? In the first example, if the limits exist but are two different limits, then it's not a continuous function and the limit doesn't exist. So also, if the limit does not exist, then the function is not continuous. And it's also going to be taken backwards. If the function is not continuous, then the limit doesn't exist. So for continuity, we have to have the limit has to exist. But is it always the case? Well, we just saw in that sine function, is sine continuous? Yeah, but it's oscillating and it goes from positive one negative. So you can't really say it's going to one specific value. In the second one, do the limits exist? Yeah, well, they do. Limit one does not equal limit two. This one goes to positive infinity. This one goes to negative infinity. And we'll talk about later on that we can say the limit of a function is infinity. But since one of them is positive, one of them is negative, that is a definite no-no. They're going opposite direction. They're going away from each other. Are they? Is that a function continuous? No, because I'm going down here, and all of a sudden I go all the way up here. And that fourth one we just talked about, the sine function. If you have an oscillating function, the limit doesn't exist because you can't tell me where it's really going. So now we have the limit laws. Let us first define that these limits exist. The function f of x approaches L as x approaches C, and the function g of x approaches M as x approaches some value C. So these are the limits. The first rule is called the sum rule. If you have the limit as x approaches C of the sum of two functions, then what this says, because I'm taking the sum of two functions, I can take the limit of both of these functions separately. The limit of f of x is L, and the limit of g of x is M. I could do that way. That's what it's telling me. This is, what if you had a long polynomial with 8 terms? You can take each one of them separately or treat them as one big long function. And the converse of that one is the difference rule. The limit as x approaches C of two functions that are subtracted. I can take both of these functions and split them up. The function of f of x is L and g of x is M. The constant multiple, you'll be using this one a lot. What this one says is if I have a limit of a function multiplied by some constant, because the limit looks at what happens to that value as x approaches a number, since the constant doesn't have an x value, it serves no purpose inside the function. So we can take the constant function out. So it becomes the constant function times the limit. Again, this is another thing we'll be using a lot of in this course and the next two courses after that. So if you have a constant coefficient, you can take it out and just worry about the function itself. The fourth one is the product rule. I'm taking the limit as x approaches c of the product of two functions. I can split them up. And then I just have the product of each individual limit. Again, now why is this one so cool? Is what if I have a binomial? I can split this up in two factored forms, and I can do both of those separately. They'll be a lot smaller, a lot easier. The opposite of the product is the quotient. Quotients are fractions. So if I have the quotient of two individual functions, what has to be true here is g of x cannot be zero. Whenever you have the denominator can never be zero. So what this says is I could take the limit of both the top and the bottoms separately. As long as the limit is not equal to zero. The sixth one is the power rule. What this one says is if I had a limit as x approaches c of some function raised to a power n, I can take the limit of the function first and then raise it to that power. And the last one The power and the root rule are pretty much the same thing. Because remember, whenever you have a radical, this is the root, and that's the exponent. We can rewrite this function as that, as a rational expression, where the root goes on the bottom. So that's the transformation we can use. So what this one says is if I can take the limit as x approaches c of some function, root power of some function, I could treat them both separately. Or you could have done it up here. We could have done this one was the limit as f of x is 1 over n. Now we're back to this rule. Okay, what's our next example? Example 5, let's look at some of these limits. Example 5. Use the abbreviations k equals k, x equals c as limit laws in theorem 1 to find the following limits. So what does this mean? Basically is that's what we're approaching. So let's look at the first one. Example 5. A. X cubed plus 4x squared minus 3. Okay. Is it? I got to fix that too. Hold it. Really messed up this example. These, the limit of k equals k as x approaches c, and the limit of x as x approaches c is c. That's what it should read. So what this one's asking us to do, find the limit as x approaches c of x cubed 4x squared minus 3. So which rules am I going to use to solve this one? If you think about it, the sum and difference rule is like a distributivity rule. I could pretty much distribute that limit as x approaches c of x cubed plus the limit as x approaches c of 4x squared minus the limit as x approaches c of 3. So what does this one become? The limit of x cubed as x approaches c, what does it become? What this is now at this point, I just make x equal c. This one becomes 4c squared. And what does the last one become? Yeah, it's a constant. X to the fourth plus x squared minus 1 divided by x squared plus 5. Find the limit of that one. Which rules am I? Remember, what this is looking for is I'm looking for the limit as x approaches c of that entire function. So what rules am I going to use? What's that? What are 1 and 5? Yep. 1, 2, and 5. Because we have a difference also up here. So the first rule we're going to use is the quotient rule. The limit as x approaches c of the top number over the limit as x approaches c of the bottom number. So we have to first implicate the quotient rule, because we have to split them up. Now what we have here, we can use the sum and difference rule. Distribute that one over. So on top, we get the limit of x to the fourth plus the limit of x squared as x approaches c minus the limit as x approaches c of 1 . So the limit of x to the fourth as x approaches c becomes c to the fourth plus c squared minus 1 over c squared plus 5. Well, I'll talk about that in a second. And c. Let's look at c. The radical of 4x squared minus 3. What it's asking us to find is the limit as x approaches c of radical 4x squared minus 3. So what's the first thing you want to do there? What's that? The root, yes, convert the radical to an exponent. So the first thing we're going to do what number is inside the root? 2. Right, so it's about 1/2 power. So now what this thing says, so I'm going to distribute inside there. So we have the limit of 4x squared minus the limit as x approaches c of 3 to the power 1/2. This, we use the constant rule. So the 4 goes out in front. X squared it's a constant coefficient. So the limit of this part becomes c squared minus the limit of 3 is 3. And there's your answer. Okay. As x approaches c, as x approaches c, as x approaches -2. So well, for this one, we're going to -2. What do we get? So as x approaches -2, that is our c value. So in here, -2 squared minus 3 -2 squared is 4. 4 times 4 is 16. Is there a faster way we could have done this one? All these? What would that be? What would the faster way be? Right off the bat. I mean, if you think about it, every one of these, if we just took the original equation, put c in place of x, and that will tell us what's going to happen. If it works, it works. If it doesn't work, it doesn't work. Yeah, so the first step you really want to do when we do limits, if it's to a value, plug it in there, see what happens. If it gives you a value, you're done. If it gives you something weird, like 0/0, or something's undefined, then we have to do other things. Okay. evaluating limits of polynomial and rational functions. So what these theorems labor to produce are the obvious we just did with the laws. If you have a polynomial, multiple parts, you can take the limits of each one of those separately, which is what we just talked about. Just plug in the value of C in place of all the X's. That's what that says. Just if you have a large polynomial, just plug in there, see what happens. Same with the rational. If you have two functions, first plug in the values, whatever your limit value is, see what happens. If it works, it works. If it doesn't, it doesn't. And you have nothing else to worry about. Yes.
What's the limit? Like it'll be like X approaches -2.
Yes. Yes. Like for example, here, it has to be given. So this will be X equals. Typically, that's a very good question. When you have limits, these questions, okay, it's going to ask you, but in reality, if you're looking for a limit function, what you would do is take the bottom function, set it equal to 0, and see what value that is, and that's usually the limit you can go to. But sometimes, like some of like this, they'll give you a value. So if they give you a value, first thing you want to do, let's plug it in there, see what happens. And again, if it comes out to an answer, you're done. If it gives you 0/0, then we have other things. If we have 0/0, that's actually to me a better sign. Well, no, it's not. It's not better. It's the second best, because that means something can happen. Either I can factor it out algebraically, or there's another procedure we can do, and we'll talk about that a little later. But if you have 0/0, it's not end of the world. We could do something else. So what would you do here with this example? Example 6. We have the limit as x approaches -1 of the quotient x cubed plus 4x squared minus 3 x squared plus 5. If I gave you that function, what would you do first? Just plug it in, right? So plug it in there and see what you get. And algebraically, if you have a negative number inside a parenthesis, if the exponent is odd, then the answer will be negative. If it's even, it's going to be positive. So since these are ones, all I do is just put a -1. That one doesn't change. That one doesn't change. So we have -1 plus 4 minus 3 over 6. 0/6. What is 0/6? Don't calculators. Oh, not in this class. You're going to use a calculator for this one. Yes. Is that what you were checking?
Yeah.
No. Okay, let's talk about that. So 0/6 as opposed to 6/0. This how many times does 6 go into 0? It doesn't. How many times does 0 go into 6? How many times can I give you nothing? So my promise to you all is for Christmas, I'll give you nothing. So the rest of your life, I'll keep my promise. So that's where we get the two values. So this is why it does not exist or undefined. So far, so good. So the first step is just plug it in there, see what happens. If you get 0 on top, that's good. If you have a fraction and you ever want to find the intercepts, just set the top equals 0. If you have a fraction, a rational equation, and you want to find the x-intercepts, remember the x-intercept is y equals 0. The only way the function equals 0 as a fraction is if the top is 0. So if you have a fraction, you want to find the x-intercepts, set the top equal to 0 and solve it. The next part, eliminating common factors from 0 denominators. That's kind of what we did in our first example. The x squared minus 1 over x plus 1. So let's look at this one. Remember, what x value would make it equal to 0 on the bottom? Yeah. So the limit as x approaches 1. Because that's always going to be your point of interest. As we see here, 1 is our asymptote. And vertical asymptotes set the bottom equal to 0, and those are your vertical asymptotes. So let's look at this. Example 7. We have the limit as x approaches 1 of x squared plus x minus 2, x squared minus x. So step 1 would be what? Just plug it in, see what happens. So we have 1 squared plus 1 minus 2, 1 squared minus 1. One squared is 1, 1 plus 1 is 2, 2 minus 2, 1 minus 1. Again, if you have 0 over 0, that is a great sign, which tells us, let's do something algebraic first. Can we factor the top? Let's try. So we know we have x squares. What signs go in there? Because the second sign is a minus, that means we have to have opposite signs. Because I said that last number is made up of those two multiplied together, and it has to be negative. And this first one says the bigger of the two numbers has to be positive. So what times what is 2? When you subtract them, you get 1. 2 and 1. And the 2 goes in the positive, 1 goes in the negative. Can we factor the bottom? Yeah, they both have an x. We take out an x, we have an x minus 1. So we can remove these. So we have a removable discontinuity. Remember, at 1, that was our asymptote. So we got rid of the asymptote. So now we just have the limit as x approaches 1 of x plus 2 over x. 1 plus 2 over 1 is 3. So the limit of that function is 3. Any questions? So if you have 0 of 0 in the first, when you first plug it in there, algebraically manipulate it. See what happens. and then do it again, and then plug it in there again. And if it is zero again, then there's something else we can do. Because whenever it's 0, that means something has to be the same. Something has to be able to come out. It means we didn't go all the way. Okay, the next section here says using calculators and computers to estimate limits. So this one, the only value we don't want is if x is equal, x goes to 0. In other words, if you use a calculator or computer, what this would do, you would do a whole bunch of numbers and see what happens. You would do from x, let's say you're using Excel, you'd go from x equals -10, decreasing down to 0. Would get smaller and smaller, 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 smaller. So the x's you would use, you'd go from -1 to -0.9, -0.8, -0.009. The smaller you make x, the more accurate your answer is going to become. Because it's going to 0, we want to see exactly how close to 0 we can get. And these values, we would eventually approach to our limit value. But that's using calculators. Do we use calculators all the time? I don't. But you can, you're more than welcome to use graph. But let's look at how do we solve this one if we didn't use calculators? Well, actually, if you notice, this is the same one here. Since I don't really use calculators, or I mean, I build design computers, but I don't like using them to do work. So example 8 says use calculator and computer and see how close we can get to 0. Example 9 says, let's do it algebraically. Let's see what we can do to it. Oops. So examples 8 and 9 is the limit as x approaches 0, x squared plus 100 minus 10 over x squared. All right, first thing we do is what? Plug them in there, see what happens. We got 0 plus 100 minus 10 over 0. Square root of 100 minus 10 over 0. 10 minus 10. So we get 0 over 0. So we know it doesn't work for sure. So there's something we can do algebraically. Actually, okay, next time I will put together an Excel spreadsheet and I'll show you how to program this kind of stuff in there. I can do it now if you want me to, but to me, it's just waste time. We can do it this way. Algebraic is faster. So if you have something like this, we have to rationalize the numerator. What makes this thing 0 is on top. Is this is equal to this. So whenever you have that, multiply by the conjugate of wherever the radical is. What is conjugate? Change the sign between there. And we have to do top and bottom. Why do we do it top and bottom? It equals 1. Yeah. All we're doing is multiplying by 1, which means we're not changing anything. We're just changing the way it looks. Now, on top, the bottom is just this times this. It's on the denominator, whenever you do something like this, never touch the bottom because that's the simplest form as you can get. So on the top, we FOIL. Radical x squared minus 100 times radical x squared 100 is what? It's the radical x squared minus 100 squared. Positive times positive is positive. 10 times radical x squared minus 100 minus 10 times radical x squared minus 100. Negative times positive is negative. 10 times 10 is 100. So far, so good. I'll let y'all catch up. Whenever you get rid of parentheses, the first thing you always want to do is simplify. We got rid of the parentheses on top, so now we got to simplify. Can anything combine? Yeah, that and that cancel. What happens here? The square root squared, what happens there? They cancel. Square roots and squares cancel. So we just have x squared minus 100 minus 100 over x squared square root of x squared minus 100 plus 10. Here. Oh, yeah, inside, yes. Yes, thank you. So that's plus, yes. Thank you. So the hundreds cancel. That was going to get me in a real world of hurt. So the hundreds, so all we have left is, as x goes to 0, x squared over x squared plus 100 plus 10. The x squares cancel. We have 1 over x squared plus 100 plus 10. We finished all the algebraic stuff, so plug in 0. Anywhere I see an x, put a 0. So we have 1 over square root of 100 plus 10. 10 plus 10. The answer is 1 over 20. Thank you for, who caught that? Good, thank you. That's what I was saying. Where did I go wrong? Yes. Always write the question down right. What's our next example? Computers, no. No. We're not going to do computers. Oh, the last thing, the sandwich theorem. This last thing is muy important. It's probably one of the most important things that's going to save us so much time and effort. It's called the sandwich theorem. The sandwich theorem says this: the following theorem enables us to calculate a variety of limits. It is called the sandwich theorem because it refers to a function f where we have a function we're looking at that's sandwiched between two other functions that we know how they behave. So that's what the saying is. You have a function f of x, but you don't know what happens to it. But we have two other ones that we do know what happened to them at a certain point. And because that middle value is right between them, whatever they go to, that one has to go to. So that's what the sandwich theorem is saying here. We don't know what happens to f of x. You see, notice how squirrely it is? But we do know h and g. We know at this value c, they both have the same value. And so does f. Since f, g, and h both all have the same value at that point, that means because of the sandwich theorem, the limit of f of x has to be L. And that's what this is saying. So let's look at these examples. Given the function, there's a limit here. X equals for all x not equal to 0, find u of x. So what can you tell me about this function? So at what point are these two equations equal? Again, this is where you get our calculator out, our graphing thing, and look at them. You look at where do these two equations overlap? Because wherever they overlap, this one, since it's between them, so you see the u function. We don't know what it is, any function, but it has to be larger than this one. So here's the bottom one, 1 minus x squared over 4. This is the u function, and this is the higher one. This is the 1 plus x squared over 2. What we do is look at what point are both of these functions equal. So let's look at that. One minus x squared over 4 is less than equal to u of x is less than equal to 1 plus x squared over 2. So first thing we're going to do is, since we're given two functions, let's see where they're equal. If we subtract 1 from both sides, that's gone. So we have negative x squared over 4 is equal to x squared over 2. Multiply both sides by 4. That gets rid of the denominators. move this one over, so we have 0 equals 2x squared plus x squared. We can factor out an x squared, 2 plus 1. Divide by 3. So x squared is equal to 3 square root. So we have x is equal to plus or minus square root of 3. No, that's 0. So x is equal to 0. Because 0 divided by 3 is 0. So the only points where these two functions have the common value is when x is equal to 0. So far, so good. So when x equals 0, what is the y value that they both share? Remember, we had 1 minus x squared over 4, and then 1 plus x squared over 2. When x is 0, that disappears, that disappears. So the limit as x approaches 0 of u of x is 1. That's the squeeze theorem. We know that since the both end limits are the same at 1, the middle one has, since this limit and this limit are the same, they equal 1. The only way this could be true is if this equals 1. That's the squeeze theorem. What's that? No, the limit was 1. It's the limit as x approaches 0 of u of x is equal to 1. When I found the value of x is 0, I went all the way back, because this is where I set both these equations equal to 0. When x is 0, where are these two equal? That disappears, so they're both equal at 1. Let me see. Do we have any more examples? Yeah, let's do those. Example 11. The sandwich theorem helps us establish several important limit rules. Sine of theta is equal to 0. Let me see that. That's missing. It's for some reason these didn't print out. For these two, the limits as x approaches 0. Pretty obvious, because if we have the limit as x approaches 0 of sine theta, sine of 0 is 0. The limit as x approaches 0 of cosine theta, so cosine at 0 is 1. For any function f of x, absolute value of x is 0 applies to f of x equals 0. Right. Yeah, so the limit as x approaches 0 of the absolute value of x is equal to the absolute value of of absolute value of 0, which is 0. Duh. Basically, saying again, they just plug those in there. But we're going to get to the important one will be coming up in the next section or two is when we have sine x over x as x goes to 0. Yeah, the squeeze theorem is going to help us as x goes to 0. As x goes to 0, what do we get? Sine of 0 is over 0, so 0 over 0. Ooh, that means something we can do. Can't factor because you can't factor sine x. So this is where we use the squeeze theorem. And also, in a little bit, we're going to define another method called L'Hopital's rule. That whenever we have 0 over 0, we can use a method called derivatives, and we could find the derivative of top and bottom, and that'll give us a solution. But that'll be for next time. Okay, that's it for today. Yes.
How was the example of the sandwich you did, right?
Yes. Example 10 was, yeah. Because what it says is we don't know what u of x is in number 10. But we do know what 1 minus x squared over 4 and 1 plus x squared over 2. We know what those are, and we know that minus x squared over 4 is smaller than plus x squared over 2. So we know that this one is smaller than that one. That has to be a condition. So since this one's smaller than this one, and they both equal the same value at a certain point, then we put that one between them. Okay.